Okay, we are going to continue with a 2-sample-t-test. I want to see if you came up with a test statistic that can be used for this. We'll also talk about the confidence interval of the difference between the two means. That's actually the really interesting and important part of the t-test that many people overlook. And then we'll wrap this section up with a paired t-test. That's also an interesting derivative that can be rather useful. Okay, so what's the solution to our test statistic calculation, to our signal to noise ratio? I'm pretty sure most of you would have figured out that we put xa minus xb here, and we can actually take absolute values of this, so we don't really care whether it's positive or negative, because the t-test statistic is symmetrical and you get the same answer. But what about the noise? So the noise is a little bit more difficult. You may be tempted to put in the mean of standard error 1 and standard error 2. But that would not be quite right. And if you think about it, these are distributions of the means, right? And they both jump around. We have a small sample size for mean A, as we have in this case, and a small sample size for mean B. So they're both unreliable, and that noise actually adds up. So what we actually should do is just add them up here. That might work. So that is a valid solution, but there is actually a slightly better way to do it, and that is using the pooled variance. So you know the standard error is the standard deviation by the square root of n, but the standard deviation is also the square root of the variance, right? So if I have square roots both in the numerator and denominator, I can put those jointly, so I can also calculate the standard error as a variance divided by the number of samples. And so what I do in the pooled variance, I'm just putting those terms here for one sample and the next sample, and if I had more, I could put them all in here to get a joint estimates of the variance. And so this has a couple of advantages. So first of all, if I have unequal sample sizes, so if NA is unequal NB, then my pooled variance is actually weighted by the sample size, right? So that's a good property. This can be done for more than 2 treatment levels, so we'll see that we'll use exactly this in analysis of variance. And the biggest advantage is actually I'm increasing my degrees of freedom. So what happens if you recall the formula for the variance? That does have a division by n-1, and those two get combined here in the pooled variance. So it's going to be NA plus NB minus 2. So minus 2 means that went into the calculation. Because in order to get the sum of squares, I need the mean of treatment 1 and the mean of treatment B. So what happens in the end is that pooled variance is quite a bit smaller than the added variances here. So that does increase my signal to noise ratio, so my noise becomes considerably smaller. And if you think that, well, you know, that seems like a sleight of hand, but it really is not. Because these are actually not measures of my population distributions, but they are measures of the means if I were to repeatedly sample. So if I work with a larger combined number to estimate this noise, that estimate becomes more reliable. So the pooled standard error is considerably smaller than the sum of the individual standard errors. And this does give me substantially more statistical power. And that will be especially valuable in the analysis of variance, where you compare 3 or more treatment levels. So the more you can pack in there, the better that estimate of the noise becomes. Now this does come with a caveat. So if you do it like this, this assumes that my standard errors that I'm pooling are actually not different in magnitude among the treatments. So this is the assumption of homogeneity of variances of individual treatment levels, and normally that is actually a reasonable assumption. If you think about where that noise comes from, those will in our case be different side factors, different microsite variations. So these are random elements that apply to both variety A and variety B. And so there's no reason why this should be profoundly different among those two varieties. And that applies for many experimental setups. So your noise is independent from your treatments themselves. This is not always the case, so sometimes you do find that the variances differ among treatment levels, and that is actually a problem. So in that case, you would have to go with non-parametric statistics. So if you find that your variances within treatment levels are significantly different, that is something I would not ignore. So this does not resolve itself just like the assumption of normality. So as soon as you crank up the sample size there, you don't really have to worry that much about the normality of your distribution of the means, right? Because of the central limit theory, we discussed this. Okay, so let's see if we can get this to work in R. Starting with reading in of variety A and variety B data. Let's calculate the means and the standard errors. So if I add up the standard errors, they were both around 14 point something, I'll come up with 29. So that could be my noise term. So if I calculate the t-value based on the sum of the standard errors, this will be my t-value, so 7.5 standard deviations out. So we already know that's a highly significant result. We don't even have to calculate the p-values. So let's see what we can do with our pooled variance instead. So if I just run the pooled variance here, let's see how big that is. So that's 20 instead of 29. So that's a significant improvement to our signal-to-noise ratio. So I divide by a smaller number. So that should give me an even bigger t-value. And let's look at the t-value. So if we take the two means, subtract them, and then divide by the pooled variance, we'll get 10.6. So 10.6 sigmas out. That's even better than what we had before. Now this is fine, that would work. It's just a little on the conservative side, so you can do better with the pooled variance and the assumption of homogeneity of variances. And just let's get our p-values here for the sum. So that would be 0.0001, and the one for the pooled variance is quite a bit better. So we'll move that decimal point 5 units to the left. So it's about a 7-fold improvement in probability. So that's nothing to sneeze at. And one more thing that's notable here is that we put in a degree of freedom of 6 in this particular case. Because for the pooled variance, we do have a combined 8 observations, but we also have 2 means that go into the calculation. So it's total number of samples n minus 2, and that would be 6. And let's see if our test actually works as advertised. Yep, same number, so 2.061, and that's what we got for the pooled variance. So I note here that I had to specify equal variances of being true, and that is because we have that assumption of homogeneity of variances in this particular test. Now the default in R is use an alternative method to figure out the noise term, and that is actually a little bit more complicated and advanced, but it doesn't have the assumption of homogeneity of variances. So if you have a situation where your treatments have different levels of variability, then you can still use this test and you get almost exactly the same p-value, right? So they don't use the addition that we did above. They have a more sophisticated method of estimating the pooled variance. So definitely use this, definitely stick with the default. The only reason why I put this in here is that I wanted to show you what's going on behind the scenes, right? So how this can be calculated so that you don't use this t-test function without knowing what's going on. Now the default version does have a more sophisticated method of estimating the noise component, so I'm not going to go over this, but it's not different in principle. Okay, so we have our test worked out, and the first thing I'd like to emphasize is don't use it like we have worked it out. So most people actually look at that p-value and say, oh great, I got a highly significant result, I got something great for my thesis or for a paper. But that's not the case. This part is actually not something you should be too interested in. What we really care about is this 95% confidence interval here. So what that is actually the confidence interval around the difference. It also reports the two means here, so we can just calculate what the difference between the two means is. So that's a 219 kilogram per hectare improvement of our variety A over variety B, and that's good. But we don't know if we're really going to realize this, right? So we want to know how sure can we be that that difference is real. And R is very helpful. It gives us a statistic that actually matters. So don't pay attention to this. Pay attention to this number. So if we do a one-sided test, that number gives the minimum improvement that we can achieve with 95% certainty. So I get at least 179 kilogram per hectare improvements out of it with a 95% probability. Now we could set these confidence levels differently. So if I want to be really sure, I can run it with a 99% confidence level, and that should give me a smaller improvement. So let's see if that works. So instead of 179, we now have 154. So it's a smaller value, but we can lay a stronger claim. So and if I walk through this, so these will increase. If I go to 90%, I'm still 90% sure that I can get a 189 improvement. I'm 50% sure that I get exactly that difference here. So that's my observation. But I could also err on the conservative side, right? So if I look at the 25th% confidence interval, I might get, with a 1 in 4 chance, I might get 230 kilogram per hectare improvement. Or if I'm really lucky and I look at the 10th% confidence interval, I might get a 250 almost kilogram per hectare improvement. So these are all good things that can be communicated for decision support. So it's not only the high certainty that matters, but also the potential, right? And if you don't have a prior expectation, you can also run the t-test without the alternative hypothesis specified. So in that case, let's see what we get here. Then we get two confidence limits. So what that means is our 219 kilogram per hectare improvement, that's what we observed, but between 168 and 270. So that would be where the true difference would sit. You notice that you lose a little bit of statistical power here. So if we run the same command with alternative equals greater, in that case my p-value doubles and my lower limit gets raised considerably. So here I can be 95% sure that it's 168 greater, but now just by having an expectation, an a priori expectation, that increases to 179%. And that's simply because I don't have to look at the other end of the tail, so I don't consider that variety A could also be smaller. So if I know in advance that that treatment is supposed to be an improvement, then definitely do a one-sided t-test because it doubles your statistical power. So I encourage you to use these really basic tests that we developed here. The interesting thing is that regardless of how fancy your analysis becomes and how complex it is with many means and many treatment levels and interactions and mixed models, in the end, you actually always go back to pairwise comparisons and to t-tests. And so that's an important part that you don't want to miss, because that's where the applications sit, right? So just to give you an example in a completely different context to see how widely applicable the confidence intervals and the one-sided single sample t-tests are. This is from one of my PhD students. What he was looking at is assisted migration of tree populations in Western Canada to address climate change. So we have to move populations northwards from Minnesota to Canada, and also, as it turned out, westward movements are good choices as well. So he made those recommendations, but foresters are also concerned what happens to their productivity. So we move things to match the environments better, but what happens to the productivity? So these here are probabilities that the populations I moved match or exceed the local sources. So local sources would be business as usual, but what happens if I move from Minnesota to Saskatchewan? Well, it turns out I can be 99% sure that they're at least as good as the local sources. I can actually be almost equally sure that we have a gain of 10%, and there is a better than 50% chance that I even get a 20% gain. So you can walk people through all these different scenarios in a very compact way from a rather big and complex analysis. These are the actionable scientific results, so people can work with that. So in that case, we preset what we want. So it's a preset value, and then we calculate probability. So it's a single-sided one-sample t-test. But you could also work with confidence intervals, just as I showed you in the example in R. So think about how you would put your results with different relevant threshold or different preset probabilities so that they can actually be used by decision makers, practitioners, and scientists. So if you look what this paper got cited for, it's usually statements that flow from this table. So without that, this study would have had no impact. So people don't care about all this fancy stuff that went on before. This last table here, that is what counts. So don't miss out on that. And last but not least, I want to cover an interesting variation of the t-test in this section before I let you loose on the lab. So this is called a paired t-test, and that is used in a situation where you have before and after measurements on the same subjects. So this could be, for example, a plant inventory before some disturbance event and after some disturbance event, or it could be something like a knowledge assessment at the beginning of the course and after the end of the course. So what happens here, if you run this as a normal two-sample t-test, you have a lot of noise because your participants have inherent variation. So some people know little in the beginning, some people already know quite a bit, but they all drift into one direction, hopefully. So they may all know a little bit more afterwards. So if you run that test as a regular two-sample t-test, that initial state of affairs, that's part of your noise, right? And that continues on into the second distribution as well. So what you can do, and that's a really clever move, what you do is you just calculate the difference of before and after, and you analyze this as a one-sample t-test. So in that case, your null hypothesis is that there's actually no improvement. The assumption is that the difference is 0. But then you plot out all the differences. So if they all make a similar type of improvement regardless of where they started, then the distribution of the differences, that is much smaller than the distribution of the original sample. So you're reducing your noise. The signal stays the same, but the noise gets reduced substantially. So it's another way of improving your signal-to-noise ratio. So that simply becomes a one-sided t-test against an arbitrary threshold, which in this case is a 0, and that becomes very powerful. So to round this video off, I do want to just recap a bit of the new vocabulary that we covered and what that means. So starting with the standard error, we've now encountered that in various contexts. So standard errors always refer to the variation of a statistic. So it's not about the original data, but about the statistic, and it is a standard deviation. So it's a standard deviation of means if I were to repeatedly sample, or it could actually be the standard deviation of standard deviation. So if I were to repeatedly sample, calculate the standard deviations of my samples, then the distribution of those values, that would also be a standard error. Confidence intervals come in the context of where the true population parameters are. And that is really nothing different than a standard error multiplied by some factor. So the standard error captures 68% of the variations of the statistic. And if I want a 95% confidence interval, then I have to multiply this by some factor. And that factor is the t-value. So that is simply to get a desired probability range. And t-value we have also now understood as a signal-to-noise ratio. That's a test statistic. And it's calculated as the difference between two means, or between the mean and an arbitrary threshold, divided by the standard error. And then finally, the p-value is the probability that I observe equal or larger difference just by chance alone. So that the difference I see is actually a sample artifact when there really is no effect. And there are also some derivative terms. So alpha level has to do with the p-value. It's a preset p-value used to calculate the confidence interval or the upper and lower bounds of a difference. So if I'm interested in whether a particular mean is above a certain threshold that's of interest with a particular certainty, then that certainty is that alpha level. And the critical t-value, I'm actually not quite sure if I mentioned that, but we calculated it. So it's a t-value corresponding to the alpha level, and it's also used in statistical hypothesis testing. So if I exceed this critical t-value, I reject my null hypothesis. So we'll get to this in the next video. So with this, you got everything to complete lab 6, so that's where you can get it. So work your way through this if you haven't started it, or do the last 2 sections if you have already done the one-sided and the confidence interval sections.